partial specialization somewhere, so that completely changes the syntax. So this doesn't happen usually in code, but as an auditor you have to check it. So one case that everyone knows is if you call sort, then you're supposed to give the ordering with the operator, the comparison operator, right? So in this case it's obvious, you call sort and this operator somewhere completely else changes the meaning of sort. But the whole of STL is just a pile of templates. So if anything is overwritten, it could subtly change the meaning of what you are calling. So in all cases, you have to chase all the code and really look at everything. So what if foo references some class? Then a bar could be virtual function too, not just a normal member. It could be a virtual member function. So then you have to see which one is called. And this is a runtime decision. It's not a compile time decision. So just by looking at the source code, you don't know. You would have to know what kind of instantiations there are in the whole project, right? So the next context you need. And you can see this mushrooming to this huge thing you have to check. And if you have inheritance, that's a little known fact that many people don't know. If you have inheritance and you have in the base function, in the base class, you have some function called foo, and in the inheriting class, you have a different function called foo with a different signature. Let's say the old one takes an int and the new one takes a string, then the old one is gone, even if the signature was different. So all this stuff you have to check really makes auditing hard. And then it could be overloaded. So that's even worse than templates. So we would have to check which one of the overloaded versions accept int. And we're not done with that because there could be overloaded versions with default arguments. So we'd have to check for int, comma something equals whatever, default arguments. And then there could be ones that don't actually accept int but something else, but there is a type conversion defined to int. Right? So this statement looks really simple, but if you just enumerate all the stuff you would have to check to understand what it does, you can see this being a nightmare. There could be implicit type conversions in the assignment too. Maybe this returns a Nord and then not a buzz, and then the type is converted, and there might be several steps in this too. And the assignment operator could be overloaded, and this could be overloaded, the reference operator. And in fact, even the brackets could be overloaded. And maybe the types don't match well, and then you get a temporary object that's constructed, assigned, and destructed. And then suddenly, if it's using auto PTR, you can see this falling on its butt, right? So, and there could be preprocessor, but I'm excluding the preprocessor because that would be a different talk. I agree that the preprocessor needs bashing, but not in this talk. So, even if you understand the code enough, then code auditing or penetration testing usually involves that you find some kind of problem, and the question you have to ask is this exploitable? So let's say I find this obvious buffer overflow somewhere, and how do I trigger this? And this can be difficult in C if people use function pointers and stuff, but in C++, this is really, you need all kinds of runtime states, so you can only really tell if you have a debugger, because looking at the code, this is practically really hard to answer. So I've mentioned reference a couple times. References really make auditing bad, and this other example kind of puts it on the point. So let's say I have some code that calls some function and passes one integer, and this integer is used as an argument to some memory allocation down the line. And I want to know if this is an integer overflow or not, right? So then I go from the allocation up in the code and see where the int is assigned or changed. And in C, at this point, it's not changed, because this is passed by value, not by reference. If you want to pass it by reference, you would have to pass a pointer, and then there would be an ampersand. But in C++, it could be reference, and you can't tell. So to see this, I would have to chase this function with all the crap I showed you. It could be like overloaded, default arguments, templates, namespaces, whatever. So this is really painful to find problems in C++. And even if we agree that reading C++ is hard, the whole language is too powerful, really. And if you look at STL errors, you get this analogy. It's not fair, really, but it looks like this kind of high-level C compiler that doesn't actually check anything, but just generates assembly code. And if you give it bad C input, then it just generates bad assembly code. So the STL error messages really look like a a tool like a couple iterations down in the pipeline, which doesn't have any of the context, just tells you, oh, something's wrong here. And it doesn't look anything like the code that actually has the problem. And so I asked a couple of career C++ programmers how they deal with STL error messages. And what they actually do, if you watch them, is that they just fudge around a little. So they, well, let's insert something here and maybe a new line there, and let's see if this changes anything, or let's add an ampersand. And so this is how it's dealt with. No one is really capable of understanding the error messages. And I mentioned earlier that C++ is too powerful for its own good, so I try to find some places where it's really obvious. So this is lambda calculus for C++. Someone actually did this, and I tried to find out how it's done, but the code is so unreadable. I dare anyone here to find it out and email it to me, and I'll mention you on my webpage, because this, I think no one can actually explain this. So the mechanism behind boost.lambda is so-called expression templates. So the supercomputing people usually used Fortran to do their stuff, because Fortran doesn't have pointers and no aliasing, so the compiler can make more assumptions and generate tighter code. So to get the same thing in C++, people have actually tried to use templates to create a parse tree in templates. So the compiler is actually interpreting another compiler that builds the parse tree for the arithmetic expression, and then everything is inlined, right? So you have like this extra level of compile time, which takes ages, but in the end the code approaches Fortran. And so you have to understand that this code actually tries to do templates with like on-the-fly generated middle things. You can see this in this example, it's quite good. So this actually works. If you overload the slash operator and define some kind of closure class that doesn't actually do anything, but it's just the right-hand side of this expression, then you can actually define your own operators. And expression templates work kind of like this, but they actually work with plus and minus and the multiplication operator, and it's meant for matrix multiplications and stuff like math kernels. So people actually use this. I thought it's a joke when I saw the paper, but it's actually used, and it's the feature currently that promotes C++ in the scientific community. So most people, no need to mention this really, most people can't handle all that flexibility. So if you give them too much flexibility, they just shoot themselves in the foot. And this usually leads to code leaking resources, in most cases just memory, but sometimes also other stuff if someone throws an exception. And so this is a new bug class in C++, exception safety. And I have a contrived example later to show the typical failures of this. And suddenly you have to provide an assignment operator if you have a class. And people do that, but then if someone does something like this, and maybe not on purpose, but some macro or template ended up with this, then suddenly the assignment breaks down because the guy writing the assignment, who shouldn't have had to write the assignment in the first place, forgot to handle this case. This is actually pretty common. And then stumbling blocks like AutoPTR. So there's lots of flexibility, and you can see this breaking down in the marketplace, but apparently no one drew the conclusions from this. So a couple more words I have is like this. So if S is a string, standard string from the standard template library, then there's a different treatment for if the string is const or if it's not const. Because in one of the cases, it's guaranteed that there's a null byte in the end, so you can cast it, to give it as argument to legacy C string handling functions. In the other case, not. So this code, suddenly you have to see, is it const? And this is like hidden stuff. It's documented if you read the STL documentation, but that's like 400 pages, and you might as well read the phone book, right? So no one actually reads this. And even Björn Stostrup, who wrote the C++ book and the language, he says don't use this book to learn the STL. You should get someone to explain it to you. So this kind of stuff is all over the place, and no one knows it. And usually you will never hit this. I'm not saying that all of this will, most of you will never hit any of this. But if you do, it was completely avoidable. That's what I'm saying. So another word that I find really horrible is that if you want to overload the increment operator, and you just declare an operator plus plus, how does it know if it's the plus plus A or it's A plus plus? And so they decided that if you want to override A++, then you get passed in dummy int, which is like the least elegant way possible to do this. But I mean, who comes up with this stuff? There's another little known feature in STL that most people saw, but some people even try to use it. It's the allocators. So if you have like a container in C++, let's say a list, and you want to put it in shared memory, or let's say you want to put it in the graphics card memory. That's usually the two areas where people use this. Then you would have to give your own allocator. And once you do that, suddenly you cannot assign members from one of them. There's no interoperability with the same data structure, but one has the custom allocator and the other not, because this changes the type in C++. So it's the same data structure, it's just has a different allocator, and suddenly you can use like assignment and stuff. So this probably will never happen to you, because using allocators is really hard. I tried for like a week and couldn't get it to work, so I still don't know anyone who ever got this to work. If you know someone, contact me, because I'm curious, but I've never seen this work anywhere. So another one is like this: if you have a map and you use the operator to access a member that isn't there, then it's just edit. So this is not really bad, but it's kind of if you don't expect it. So you could also throw an exception, for example, right? But most people coming from Perl or something, they just do this and want to know, does this exist? But once you write it down, it exists because it's created especially for this. So there's lots of small stuff that's in itself not that bad, but the whole mess combined is quite horrible. One thing that always strikes beginners as really a big joke on C++ is that you have templates and you use more than one template in the same statement. Then you have more than one closing bracket, but you can't write them without a space in the middle, because otherwise it would be the shift operator. And this is actually so hilarious that the C standard people are changing this for the next version. So, and this means that even the Lexer part of the compiler is now integrated in the rest of the mess, and it's now no separate component anymore. Just because this, the Java people used to make fun of this, and so it had to be changed. So when you disassemble some piece of code and it was written in C++, you can usually see right away, because there's lots of wrapper functions that don't do anything. They just call something else. And this is bad, because usually when you disassemble something with like IDA or something, then you get all these functions and you start to assign names to it. And usually you see, oh, it's copying something, so let's call it copy. But if you get like the fifth function that just calls some other function, you're like, ah. So you would think the compiler is able to not generate code for this kind of function, but it turns out to be not true. So the linker is supposed to remove unreferenced code, and this is supposed to happen by just looking at the symbols that are exported. But in C++, you have a virtual function table with a virtual function that's never called because the base class is never instantiated. But during the construction, I told you, the vtable points to the base class, even if it's not actually using the base class. And the vtable of the base class references all the virtual functions, even if they're never called, right? So this pulls all the crap in your code, even if you never call it. And this is how these C++ programs become so huge. And, well, another big thing that's not only true for C++, but for most other languages too. If someone gives you a library, you have no way of telling, short of looking at the code, to find out what kind of exceptions it's throwing. So you call something and you want to know, can this throw an exception on me? Then it cannot be answered. You have to look at the code. And if you bought the code and you just have the binary code, then good luck disassembling. There's several new bug classes. So some people say this is the worst thing about C++. But I think, okay, this is bad, but, people, it's okay, I can work around this. I think the other points are more important because you cannot work around them. Even if the perfect guy wrote the code, you still have to consider all the stuff. But these are important nonetheless, so I'm at least going to mention them. So I mentioned exception safety. Then there's a subtle difference between these two delete operators. And this can lead to code execution, which is really like the worst thing that can happen to you. Then there's an integer overflow in the operator new that's in the compiler, it's not in the library. I have an example for that. And then there's local static initialization, which is that's a race condition. It's covered by a talk Lisa gives, I think in 2 days, so you should go there. Probably a really nice talk. I'm going to be there at least. So there are many horrible words in C++ that open up new problems that shouldn't be there, like expired iterators, I had that before. And pointer arithmetic on base classes. So this is also quite funny. I'll show you. Oh, by the way, it's still running, right? So.